At 3 a.m., a critical memory leak crashes a primary production server. For the last decade, resolving this exact failure relied on human intervention. An on-call DevOps engineer would wake up, log into the terminal, and physically read through the stack trace to find the bug. In traditional open-loop response, an error alert routes directly to a human. The system stops, waiting for a patch. That reliance brings the pipeline to a dead stop. Even skilled engineers need minutes or hours to deploy a fix. Modern microservice architectures generate millions of log lines per minute. This sheer volume of telemetry data outpaces the cognitive processing limits of any individual. Relying on a person to manually hunt for bugs across distributed systems creates a latency barrier that cannot be overcome with more staffing. The traditional DevOps role is structurally incapable of scaling. That latency barrier is forcing an architectural shift toward closed-loop remediation. Instead of firing passive alerts, engineering teams are deploying Auto-Remediation AI. These are active systems designed to write and deploy their own self-healing code without human input. An autonomous agent processes raw stack traces and system telemetry millions of times faster than a human operator, analyzing concurrent streams of data simultaneously. The daily function of software engineering is shifting toward building the infrastructure that enables these systems to heal themselves. This architectural blueprint illustrates how a modern closed-loop pipeline is constructed, starting with the ingestion phase. A standard monitoring node, like Datadog or Prometheus, detects an anomaly. Instead of pushing an alert to a pager, it routes directly to a specialized large language model. The monitoring software uses an API call to instantiate an AI agent the exact millisecond the error threshold is breached. The pipeline transmits a highly structured data packet containing the raw stack trace, time series metrics, and recent system metadata. Receiving an isolated error code is not enough to write a safe patch. The agent must immediately establish the broader system context. It scans the entire GitHub repository, cross-referencing the failing module against commit histories, library dependencies, and configuration files. The agent maps the overarching state of the application to ensure fixing a memory leak in one microservice won't break a database query in another. By linking a localized error to the global codebase, the ingestion phase automates the triage process. With the context mapped, the pipeline moves into the execution phase, where the agent translates its analysis into a tangible solution. The agent autonomously generates a script or application patch designed to resolve the specific anomaly. Deploying machine-generated code directly to live servers carries severe operational risk. A hallucinated variable or incorrect dependency could bring down the entire production environment. To mitigate this risk, the pipeline routes the new code into an isolated testing environment, or sandbox. Inside this contained boundary, the system compiles the code, executes the patch, and runs a mirrored simulation of the initial failure. Telemetry within the sandbox confirms whether the patch actually resolved the error condition, bringing the simulated CPU usage back to a stable baseline. If the test fails or introduces a new warning, the agent receives that feedback, rewrites the patch, and loops the simulation until it passes. This cycle of generation, containment, and validation replaces the baseline tasks previously assigned to junior engineers, like manually writing hotfixes or restarting crashed Kubernetes pods. Generating functional code is straightforward. The actual engineering challenge is establishing the trust required to let autonomous systems merge that code into production. In this diagram, you can see system guardrails acting as the definitive barrier separating the testing sandbox from the live user environment. These guardrails are a strict sequence of deterministic safety tests dictating the hard boundaries of what the AI can execute. By passing rigorous checks on memory allocation and database integrity, the pipeline guarantees the new patch won't trigger cascading failures before clearing each gate. Architecting these guardrails requires expertise in formal verification, the ability to mathematically prove a system's behavior. Because these guardrails are the final line of defense against autonomous errors, engineers with this mastery see the highest salary growth in the infrastructure sector. Modern software engineering centers on constructing the rigid governance systems that keep the AI within safe operational limits. Pulling back to view the completed blueprint, the auto-remediation pipeline is fully constructed. The system detects an anomaly, gathers global context, writes a patch, validates it in isolation, clears the safety barriers, and moves rapidly into production deployment. This complete cycle executes in seconds, repairing faults before a live user registers a drop in performance. Implementing this requires specialized knowledge: LLM integration to connect telemetry, MLOps to maintain the agent, and system guardrails to secure deployment. Knowing how to write basic CI/CD YAML files or monitor server dashboards no longer offers competitive value in this landscape. Engineering focus must pivot toward MLOps. The task is deploying, scaling, and continuously monitoring the language models that now act as the primary infrastructure operators. Preparing for a human-in-the-loop DevOps career means training for an operational model that peaked in 2020. The technological baseline has elevated. To remain relevant, engineers must transition from maintaining systems manually to governing the autonomous agents that maintain themselves.